Good morning and happy Wednesday, my fellow calculus humans. So we're going to start off today just like we did Monday with some announcements because the university has come up with some new policies since on Monday. And so the first one, let's see if we can get all of this in at once. This is massive. Can I show all this? There we go. Cool. So basically, the university is implementing a 70% rule. So what does this mean? Basically, this means, let's see, can I make this even bigger? Why is this not wanting to? There we go. 70% rule. So basically, what this says is for the final exam, if we've already done 70% of the grades, aka after the second midterm, this instructor may give students the option of taking their grade as is. So what this means basically is after second midterm, there we go. After second midterm, that would be 70%. And therefore, you don't, what's a good way? That means we can choose if we want not to take the final. We can choose not to take the final. Take the final. The problem is that the university requires that that all the learning objectives of the course have been achieved. So we need that the learning objectives are completed. Learning objectives are completed. Unfortunately, the last 2 weeks, we are going over some integration stuff, which is very, very much needed for Math 1014. And I know a good chunk of you are taking Math 1014. And so I can't fully take the 70% rule. Unfortunately, this means can't do. Unfortunately, can't use 70% rule in class because of that. But I'm going to do something slightly different. So something that should make life easier for people who are okay with their grade after the second midterm. And basically, what we'll do is the following. So our version. If you're happy with your grade, your grade after the second midterm, after second midterm, you can elect to keep that grade. There will be one stipulation though, but what's a good what's a good way to say this? But basically, for this to apply, what I'll do is I'll give a little mini quiz to make sure you're okay with the last 2 weeks of stuff. So, but for this to apply, you need to be good. You need to be good with the last 2 weeks of material. I can't spell apparently, material. And so basically what we'll do, we'll have like a little mini quiz, and we'll do this through Moodle. So if you're happy, if you're happy with grade, let Aram know by 3 April. What you'll have to then do is I'll put a little mini quiz. Take mini quiz on Moodle that covers last 2 weeks. Of class. Then if you get greater than 50% on the quiz, I'll keep your grade. So basically, keep your grade from before. Keep your grade from before. What this means is you won't need to do the final exam. You can skip the final exam if you do this. I'm sure there'll be questions on this, so feel free to ask me any question you have on this. Basically, there's the 3 steps. 1, if you're happy with your grade, let me know before Friday, April 3rd. It's the last day of class. Then we will have a little mini quiz. It will be 3 April is when it is. This is why I need you to let me know before 3 April. And then if you get over 50% on this quiz, you'll keep whatever your grade is, so you don't have to do the final. The quiz itself won't count. The quiz will probably take about 30 minutes. Because I will ask basically all the things we're going over in the end. It should be not too bad, but I just want to make sure you can actually do this. And yeah, I can give details to everyone who does let me know before the 3rd of April. So yeah, if there's questions, let me know. There's a second announcement. And that the university has changed their policy in regards to withdrawing from class. So they extended the deadline to withdraw. You can withdraw. Basically, it says you can withdraw from a course without receiving a grade and removing a W from a W transcript notation. For winter 2020. You can withdraw up until 9 May. So the deadline has been extended. Before, I think the deadline's already technically done, so they're extending it up until the 9th May. So you got tons of time for this. The deadline is also 9 May to change course to pass-fail. If you'd prefer to do that, to change course to pass-fail. So that's our announcements for today. If there's any questions, feel free to ask. And that should be it. Banana. Yeah. Okay, so let's start off today with going over apparently what wasn't saved last week. So last week we actually went over So last week I thought I had recorded this, but apparently it was not recorded. So let's go over this. And so basically what we're going to want to do for this is first thing we do is we set this equal to L. Oops, I need a pen. So we set this equal to L. And so the first step, right, is to take natural log of both sides. So I'm going to do this from up here. Oh, sorry, this is not first step, this is second step. So step 1 is to set L. Here, we should actually do like a little review. Nope, there we go. There we go. So remember what we do. First step is we set L equal to the limit. Second step, we find the natural log of both sides. We solve for the limit. And then we find what the limit actually is. So this is step 1, set the limit equal to some number L. And then we're going to take the natural log. So step 2, we'll do up here. So we take natural log of L is equal to the natural log of the limit as x goes to 0 of sine of x to x. So this, we can put the natural log inside. And we get limit as x goes to 0 of natural log of sine of x. So here, just with natural log rules, this x we can bring in front of the natural log. And so we get limit as x goes to 0 of x natural log of sine of x. So if we were to plug our numbers in and to see kind of what this is, this will give us 0. And then this is going to, so the natural log, this is 0 as well, but the natural log gives us infinity. So we have 0 times infinity. And remember, in this case, what we want to do is we take this x and we bring it downstairs. So what does this look like? What this looks like is something like this. So we have x to 0. We keep natural sine of x on top, and we bring x down and we take the reciprocal. So this is slightly confusing, but if you notice now, what we have is we have infinity on the bottom and we have infinity on the top. And we can take the we can use L'Hopital's rule, right? So therefore we can use L'Hopital's rule. So what are the derivatives? So f prime of x, so we should use this instead. So d dx of the top, sine of x. I'm missing it. There we go. This is equal to, so this is nothing more than the chain rule. So we first take the derivative of the outside, which is natural log, and that's just 1 over whatever's on the inside, so sine of x. And then we take the derivative of what's on the inside, which is just cosine of x, right? So the derivative of sine of x is cosine of x. And I'm going to leave it like this for now. And then we want to take the derivative of 1 over x, right? That's our denominator. And so the derivative here is just the derivative of x to the minus 1. So this is just minus 1 times x to the minus 2. So this is just minus 1 over x squared. So what this means is by L'Hopital, what we have is our limit as x goes to 0 of natural log of sine of x over 1 over x is equal to the limit as x goes to 0 of cosine of x over sine of x times, and then so here on the bottom we have minus 1 over x squared. So this gives us limit as x goes to 0 of x squared cosine of x over sine of x times minus. And what you're going to notice here is when we plug in, again, we will get 0 on top, 0 on the bottom, and so we have to take L'Hopital's rule a second time. So let's look at the derivatives here. So I'll do these ones here. And so we're going to get d dx minus x squared cosine of x, d dx sine of x. And so these I'm not going to do right off the bat because this is something you should have done already at home. So here we get minus 2x cosine of x plus x squared sine of x. And this is just cosine of x. So therefore, by L'Hopital, this is equal by L'Hopital to limit as x goes to 0 of minus 2x cosine of x plus x squared sine of x over cosine of x. So here, if we plug in, right, we would get 0 on top, 1 on the bottom, and therefore we cannot use L'Hopital. But what we know is, since these are continuous, so here we'll do equal here. Since our function is defined, is continuous everywhere cosine of x does not equal 0, we can plug in 0. So here we can just plug in 0 and we get minus 2 times 0 times cosine of 0 plus 0 squared sine of 0 over cosine of 0. So here we end up getting 0 divided by 1, which is just 0. But notice how this function here, this 0, is, if we go backwards, right? If we keep going backwards, this takes us up here, and we keep going backwards, and then from here, we're going to go up to here, and this is equal to natural log of n. So this is just equal to natural log of L. And so what we're going to want is, we're trying to solve what L is, right? So step 3 is you take the e of both sides. So e of natural log of L, this is just equal to L, which is equal to limit x minus over 0 sine of x to the x. And this is just e to the 0, right? So we just plug in our natural log here. So this is equal to 1. So this is just equal to 1. And we have our solution. Okay, so that's how you should have done this problem. If you didn't, that's okay. But we're going to move on now, and we're going to look at optimization problems.